Good morning, class. Today we shall be looking at another topic, AC voltage applied to capacitors. I hope you all had a good weekend, and we thank God for a new day. So I hope you have been reading and studying your books. Today we'll go on to another topic. So capacitive reactance. What is capacitive reactance? By capacitive reactance, we mean the effect of a capacitor on AC current when a capacitor is driven by an AC voltage source, as shown in this diagram. I'll pick my files. This is an AC voltage source, and this is a capacitor. So the capacitor limits the current that flows in this circuit, but does not completely prevent the flow of charge. So because the capacitor is alternately charged and discharged as the current and voltage reverse each half cycle. We'll see that shortly graphically. For a circuit with just a capacitor, as shown previously, these are plots of the AC current and voltage versus time. This is the voltage, and this is the current. What can you observe here? You can see that the current is leading the voltage by 90 degrees, or 1/4 cycle. This is 1/4 of a cycle. This is half a cycle. This is 3/4 of a cycle. And this completes a full cycle. When you take it from here, this is called a full cycle. So this is 1/4 of a cycle, and the current is leading the voltage by 90 degrees, or 1/4 cycle. Please mute yourself. I just want to find out if my colleague is here. Okay. Dr. Shakwandi, I want to make you co-host right away. Oops. Okay, done, yes. Okay, let's go on. So changing conditions of the capacitor with time. Changing conditions of the capacitor with time. We start with, let's look at the changing conditions of the capacitor with time, starting with this circuit. We have about 5 circuits to look at. So we call this figure 3, this circuit figure 3, and T is equal to 0 is arbitrarily chosen as the time of maximum voltage. T equals to 0 is arbitrarily chosen as the time of maximum voltage, V equals to V0. At the start, the capacitor is assumed fully charged with polarity shown. So it's assumed fully charged with this polarity, positive charges here, negative charges here. Because the plate cannot accommodate more charge, there is no current in the circuit. That is when the capacitor is fully charged, no more current will flow in the circuit. So this star here represents, is explained here. we have arbitrarily chosen the polarity of initial capacitor voltage as positive. So that's the first condition we are looking at. Let's look at another condition. This is the first condition. The first circuit is A. This is B. This is C. This is D. And this is E. So we are going to be explaining each one using each bullet. This one explains what is happening B. This one C. This one D. And this one E. So let's look at this circuit here. As the voltage decreases, so that V is greater than 0 but less than V naught, the capacitor begins to discharge, giving rise to a counterclockwise current. You can see that the charges are reducing. Before, you could see two positive signs here, two positive signs here, two negative signs here, two negative signs here in the first circuit diagram. But here is decreasing, current is flowing. So as voltage decreases, so that V is greater than 0 but less than V naught, the capacitor begins to discharge, and that we have seen here. In this case, the current reaches its maximum value when the voltage drops to 0 and the capacitor plates are completely discharged. You can't see any charges here. There's no charge here. So this occurs so
make I follow the man talk.
160 students.
sorry, something went wrong. So go back and share screen. So there was an interruption. Sorry about that. I don't know where it came from. Thank you, Dr. Shakwande, for helping out. So we were here. Let me pick my highlighter. Okay, fine. So for this circuit, the AC voltage source now reverses polarity and starts to increase in magnitude so that V is greater than minus V naught, but less than 0. The capacitor begins to charge again. You can see the capacitor begins to charge again, but in the opposite direction. You can see the positive signs here and the negative signs here. The capacitors begin to charge, this time with the opposite polarity. With the plates uncharged, there is no opposition to the current. So the current is at its maximum value. However, the plates accumulate charge, they begin to inhibit the current, and the current decreases in magnitude. As they accumulate charge, they begin to inhibit the current. So the current decreases in magnitude. I is less than I naught. So for this kind of situation, or for this condition, halfway through the cycle, the capacitor is fully charged, but opposite in polarity to its starting condition. the starting condition as in A. Is in the starting condition, the positive signs were here, the negative signs were here, but this is opposite in polarity to a starting condition. The current is 0, I equals to 0, and the voltage is at its maximum magnitude, but opposite the initial polarity. So V is equal to minus V naught. So something worth noting is that, okay, before we leave that slide, during the next half cycle, although it's not shown, the process is reversed and the circuit returns to its initial condition. So on and on like that. So we should take note that the current and the voltage are not in phase. They are not in phase. The current reaches its maximum a quarter cycle ahead of the voltage. So the phase relationship, go on to the next slide. So the phase relationship between the current and the voltage for a capacitor is commonly stated in this way, that in a purely capacitive AC circuit, the current leads the voltage by 90 degrees or 1/4 cycle. Okay. This is the way it's usually stated. Thus, in an AC situation, a capacitor provides opposition to the charging process, but it is not totally limiting. The quantitative is like summarizing what we have said earlier at the beginning, that, what we said here, that the capacitor limits the current, but does not completely prevent the flow of charge. Capacitor limits the current, but does not completely prevent the flow of charge. So it limits the current, provides opposition to the charging process, but it is not totally limiting. The quantitative measure of this capacitive opposition, what we call capacitive opposition to current, is called the capacitor's capacitive reactance. Capacitive reactance. So in the we denote it with this sign. So in an AC circuit, capacitive reactance is given by, I call it chi C equals to 1 over omega C equals to 1 over 2 pi FC. SI unit of capacitive reactance is ohm, or second per farad, where, as usual, omega is equal to 2 pi F, and capital letter C is a capacitance in farads, and F is the frequency in hertz. So like resistance, reactance is measured in ohms. So this formula or this equation is very important as we go on. So take note of that. So there are some inferences to make based on this. You know, the frequency dependence and the capacitance dependence in that equation are being explained here. Capacitance means charge stored by volts, per volt, sorry. Charge stored per volt. And it's given by this equation, is equals to Q over V. Therefore, for a particular voltage, the greater the capacitance, the more charge the capacitor can accommodate. This requires a larger flow rate of current. And this is very straightforward. The greater the capacitance, the more the charge, this is the capacitance. The greater it is, the more charge the capacitor can accommodate. Who is putting on video there? Miriam Yakub or Yakub? Miriam Yakub, put off your video. So increasing the capacitance offers less opposition to, thank you. Increasing the capacitance offers less opposition to charge flow. That is a reduced capacitive reactance at a given voltage frequency F. So the greater the voltage frequency, the shorter the time for charging each cycle. A shorter charging time means less charge will be able to accumulate on the plates of the capacitor, and there will be less opposition to the currents. I'm emphasizing some of these points so that to help you understand it. Otherwise, we have explained that before in the circuits, but this is to further help you to understand what we are talking about today. So I'll repeat this, that a shorter charging time means less charge will be able to accumulate on the plate of the capacitor, and there will be less opposition to the current. So increasing the voltage frequency results in a decrease in the capacitive reactance. Hence, capacitive reactance is inversely proportional to both the capacitance and the voltage frequency. If you look at the equation, the capacitive reactance here is inversely proportional to the voltage frequency and to the capacitance. So that's just what those details are talking about. So in conclusion or in summary, capacitive reactance is related to the voltage across the capacitor and the current by an equation that has the same form as V the capacitor and the current by this equation. So if you make the capacitive, if the capacitive reactance is known, we can, and we are asked to find the voltage and we are given the current, we use this formula. Assuming the voltage is known, the current is known, and we don't know the capacitive reactance, we will make the capacitive reactance the subject of the formula here. Looks like today's lecture is going to end quickly, but I want everyone to try and work out this example. A 150 microfarad capacitor is connected. Probably I shouldn't have given you the solution here already, but it doesn't matter. A good student will still try to work it out and see if he or she can arrive at these solutions. So the question says a 15.0 microfarad capacitor is connected to a 120 volts, 60 hertz source. What are A, the capacitive reactance, and B, the currents, RMS and peak in the circuit? Again, a 150 microfarad capacitor is connected to a 120 volts, 60 hertz source. What are the capacitive reactance? And B, the current, RMS and peak in the circuit. So the formula you need is given in equation 1 and equations 1 and 2 and equation 5 that we had last week. So the capacitive reactance can be obtained from the capacitance and the frequency by using equation 1. This is equation 1. This is equation 1. Then for B, we can then calculate the RMS current and the reactance and RMS voltage using this equation 2. Finally, we are going to calculate the peak current using this equation 5. It was equation 5 last week. This one was equation 5 last week. Even though it was also written as IRMS equals to 0.707 I naught. So today, if you make I naught the subject of the formula of that equation 5, you have this. So I want you to confirm these solutions. Use your calculators and work them out. If you will arrive at the same solutions. We have to find the capacitive reactance, the I naught, and the IRMS. So the first step in answering any question is to try to understand what is the question telling me to do? What am I asked to do? A is very straightforward, okay? Capacitive reactance, you know the formula and all that. Then the current RMS, the current peak. What is current peak? Is I naught. I naught is the peak current. Somebody might be wondering, oh, what's the peak current? I naught is the peak current, IRMS is the RMS current. So you have been given these constants, these values. Remember that you have microfarad. What is micro? Micro is 10 raised to the power minus 6. So you have to, anywhere you see micro, milli, you must evaluate that before you continue with your solutions. Some people make that mistake. They will go ahead and use 15 farads to calculate, forgetting that this micro here represents a value, and the value is 10 raised to the power minus 6. So in any calculations, in any problem you are given, if you find something like milli, centi, or whatever, micro, you must first evaluate that. I mean, write out what the value is before you carry out your calculations. Otherwise, you'll be getting the wrong answers. So practice this now. Okay. So I would want everyone to try this out for the remaining time for this lecture. As I said earlier, I'll be stopping here today because I have some things to attend to, which are also official. So next class, we'll be discussing inductive reactance. Like looking at the behavior of inductors in AC circuits. We are going to be calculating the effect of inductors on AC current. So we'll look at that next class. If you have your comments, your questions, you can send them as messages. Somebody thinks that the capacitive reactance is 17.68 ohms. Somebody thinks, just keep thinking whatever you think, okay? Just keep working it out, okay? I'll leave it there for a while so that you can copy it or write it out in your notebooks. If you think this is not the correct answer, just keep sending your messages. But some people agree with this, some people don't agree with this value, but whatever. You remember you have to, sorry, let me pick my spotlight. Remember, you have to evaluate pi. You have to write out what pi is. Okay, you have to write out what pi is. So if you are evaluating, if you are trying to evaluate this without making room for what pi is, you'll be getting the wrong answers. So I just went through your chat now. Some people are saying this is not right and all that. So just keep working it out. Somebody is showing us his bedroom. 222. Well, write it out. I'll leave it there for 1 minute, then I'll take it off and end the class. Send your messages. Send your questions as messages, send your messages, send your values. If you agree, if you don't agree, send your values. Just send your comments as messages. I hope you have written the question. Just write the question and work it out. Use equation 1, equation 2, and the last equation 5 of the last lectures. I'm going to end the lecture here today. So see you on Thursday. Thank you.